Welcome to the 14th video of our lecture series. So in this lecture series again we are going to solve some problems. So this is our first problem. So it states that we have a particle of mass m and it is in the potential of this kind. So we have to find the energy eigenvalues according to the WKB approximation. So first we have to know what is WKB approximation. So according to WKB approximation, P dx is n plus half h cut, where this sign represents closed loop. So what is the form of this potential? So potential is Ax. So we can draw this potential as this. So this is our potential as a function of x. And suppose we have our energy value somewhere here. So an energy value will be somewhere here. So it will be confined in this region. So we can write our energy P E to be P squared by 2m plus potential. So we can write this as alpha x. So from here, if you want to calculate P, it will be root under 2m e minus alpha x. So what will be the value? It will be P dx, or so in one dimension you can write this as P dx. So Q is for generalized coordinate. So P we have root under 2m e minus alpha x dx. And for this, what will be the integration limit? Integration limit will be from this point, So how to find these points? So at this point and this point we have E to be alpha x, because at this point the potential energy is equal to the energy. So if you want to we will find the value of x to be E by alpha. So the integration limit is from minus E by alpha to plus E by alpha. And according to WKB approximation, this term will be equal to n plus half h cut. So let us, from this integration, we have to find the value of E. So let us proceed. So we have minus E by alpha to E by alpha, and here we have 2m E minus alpha x dx. So we can write this as from minus E alpha to 0, in this limit mod x we know that it is x for x greater than 0 and minus x for x less than 0. So here it will be minus x. So we can write this, and in this integration limit we can write this as mod x will be plus x. So we will get this integration. So now look at this integration. So if we replace x, suppose we replace x by minus t. So what we will get? So integration limit is from e by alpha to 0. Here we have 2m e minus alpha t, and dx will be minus dt. So minus dt. So this can be written as 0 to e by alpha 2m e minus alpha t dt. Now t is the integration variable, so we can change it to any value. So if we write x in place of t, then we have e by alpha 2m e minus alpha x dx. So this integration is same as this. So we can write this term as 2 0 to e by alpha root under 2m e minus alpha x dx, and that will be equal to n plus half h cut. So we have to evaluate this integral. So now let us replace this term. So let us consider this to be t. So what will be the integration limit? So when x is 0, we have our t to be 2me, and when x is e by alpha, we have our t to be 0. So, and whenever we have dx can be written as minus 1 by 2m alpha dt. So this we can write as 1 by 2m alpha, and for the minus sign we can interchange the limit. So the limit we have 0 to 2me, and here we have root under t dt. So that is equal to n plus half h cut. So this will be t to the power 3 by 2 by 3 by 2. So that means 3 here and 2 here, and the limit is from 0 to 2me. So t we know is 2me to the power 3 by 2, and here we can write 3m alpha by 2 n plus half h cut. So from here we can write e to the power 3 by 2 as 3m alpha by 2 product with 2m and root under 2m. So we have an m term to be cancelled out. So we basically have 3 alpha n plus half h cut by 4 root under 2m to the power 2/3. So that is our energy value. So let us check. Three alpha h cut so option B is our correct answer. So you can be given with any form of potential, and so for the WKB approximation we have to know that this P dx can be replaced as n plus half h cut omega, and from the Hamiltonian we can replace the P, and we can find so the integration limits. So what will be the integration limit? Whenever we have potential energy equal to our total energy, that means when the kinetic energy of the particle is 0. So that is basically the turning point. So by finding this integration limit and evaluating this integral, we can easily calculate the corresponding energy. So now let us move to the second problem of today's video. So what the problem states? It states that we have S1 and S2. These are the two spin operators of two electrons in a helium atom. So we have to find the expectation value of S1 dot S2 for the ground state. So first of all, we know that the value of the spin of an electron is half. So we have two electrons, so S1 value, this is half, and S2 value, this is half. So we have two electrons in a helium atom with these spin values. So we have to find this S1 dot S2 and expectation value, and this is for the ground state. So basically this problem belongs to the addition of angular momentum. Because we have two different electrons, so they belong to two different subspace, so we have to add them and to express their addition in product space. So if S is the total angular momentum, then we can write according to the addition of orbital angular momentum as S1 plus S2. Now S1 and S2 values are half. So what can be the values of what are the values of S? So S can have values from S1 minus S2 to S1 plus S2. Now since they both are half, so it can either have 0 value or 1 value. So S value is either 0 or 1. So now we can write this as S squared equal to S1 plus S2 squared. So it will be S1 squared plus S2 squared plus 2 S1 dot S2. So S1 dot S2 can be written as S squared minus S1 squared minus S2 squared by 2. So now we know that S squared, S1 squared, S2 squared and Sz, they are simultaneously diagonalizable. That we have learned from the general addition of angular momentum, that J square, J1 square, J2 square and Jz, they are simultaneously diagonalizable. That means commutator relation of any of these two will be 0. So since all of them are simultaneously diagonal, so they share the same eigenstates. And let us assume the state to be S, Ms, S1, S2. So in this basis, all this S square, S1 square and S2 square are diagonalizable. So if we have to find the expectation value of S1 dot S2, then we can find the expectation value in this basis. Because if we consider this basis as all of the three S square, S1 square and S2 square are diagonalizable, then our problem will be easier. So S1 dot S2, S, M, S1, S2. So this S1 is and S1 is 2, we can write this as S square minus S1 square minus S2 squared by 2, and we have S, M, S1, S2. So now we have S values to be 0 and 1. And so first let us evaluate this value for this state is 0. So 0, we have Ms value will also be 0, S1, this S1 value is half, so we can write as half, half. Now what is the eigenvalue of this? So s square s ms s1 s2, this will give us s into s plus 1 h cut square and s ms s1 s2. Similarly, what is the eigenvalue for s1 square? S1 square eigenvalue is s1 into s1 plus h cut square, and s2 square eigenvalue is s2 plus 1 h cut square. Now note that in all these eigenvalues there is degeneracy of ms. Because whatever be the value of ms, these eigenvalues doesn't depend on them. So in this problem, we don't have to be concerned about the value of ms. Whatever the value of ms be, our eigenvalues will remain same. So first let us so this will give us 0 plus 1 minus half plus 1 into 2 h cut square by 2. So what we will have? We will have minus half into 3 by 2 h cut square. So it will give us minus 3 by 4 h cut square. So this is the value of this expectation value of this operator for s equal to 0. Now what will be the expectation value for s equal to 1? So for s equal to 1, s1 dot s2 will be, so I am just writing the value ms here, because ms value we don't need to consider. Of whatever be the ms value is, expectation value is will remain same, because this eigenvalues doesn't depend on ms. So we have s1 and s2. We have our this operator. Here we have the same state, 1 ms half. So what will be the value? So we will get s into s plus 1 minus s1 into s1 plus 1 minus s2 into s2 plus 1 by 2, and we have h cut square here. So what we will get? We will get half into 2 minus half into 3 by 2 into 2. So we are getting half into half h cut square. So we have h cut square by 4. So the expectation value of this for s equal to 0 state, we have minus 3 by 4 h cut square, and the expectation value of this for s equal to 1 state, we have h cut square by 4. But we have to evaluate this for the ground state. So for the ground state, we will have minimum energy, and for the ground state we know that s value is 0. So for the ground state, we have the expectation value to be minus 3 by 4 h cut square. So our correct option is B. Now let us move to the third problem. So we have a problem that the wave function of a particle in one dimension is denoted by psi x, and so it is in the coordinate representation, and in the momentum representation we have psi p as this. So we know that this position and momentum coordinates, they are connected by Fourier transformation. So if we have position coordinate, so we wave function in position coordinate, we can convert in wave function in momentum coordinate by this Fourier transformation. So e to the power minus I px by h cut dx. So this is how we can get from position coordinate wave function to momentum coordinate, and vice versa. So we have this. Now we have the operator t, and the action of the operator on psi x is if we apply the operator on psi x, it will just move the x to x plus a. So we have this action of operator on psi x. Now we have to calculate what is the action of this operator on psi p. So we have to calculate this. So how we will proceed? We will proceed the action of this operator on psi x, and we know a way to convert this position, this momentum representation into position representation. So we will proceed that way. So we will write psi p as psi x e to the power minus ipx by h cut dx. So we have p psi x e to the power minus ipx by h cut. Now what is t psi x? T psi x will be psi x plus a, and here we can write x plus a by h cut and e to the power ipa by h cut. So we are since here we are getting x plus a, so we are deliberately making here x plus a, and we are subtracting that term. So this we can take outside. So we have e to the power ipa by h cut. Now if we replace this x plus a by another coordinate, say y, so what we have? We have psi y e to the power minus ipy by h cut dy. So since y is a variable here, we can replace this by x. So we have psi x e to the power minus ipx by h cut dx. So but what is this? This is, we know that it is our phi p. So we are operating this operator on phi p, and we are getting this. So what is our what is our this translation operator, this t operator on momentum space? Momentum space, it is ipa by h cut. So what will be the answer? So we have ipa by h cut phi p. So this will be our correct answer. Okay, now let us move to the fourth problem. So we have the product of, we have to calculate the product of the uncertainties Lx, Ly for a particle which is in the state this, where this 1 1 they represent the L value and M value. So and we know that this, since this is Lm, so this is an eigenstate of L square and Lz. So we have to find the relation between A and B, or the values of A and B, for which the product of this uncertainty Lx, Ly, this will be minimum. So we have our state psi, which is A 1 1 B 1 minus 1. So this is our Lm state. Now we have to, for this state, we have to calculate delta Lx and delta Ly. Then we have to find the product, and we have to find, after finding this product, we have to find the value of A and B for which this product will be minimum. So let us proceed. So first of all, we have to calculate the uncertainty. So delta Lx we know is Lx square average minus Lx average squared. So this state Lm is not an eigenstate of Lx. So for making the calculation easier, we will replace this Lx with the help of raising and lowering operator. So L plus and L minus. So we know raising operator is defined as Lx plus ILy, and lowering operator is defined as Lx minus ILy. and the action of this raising operator on a state Lm is root under L minus m into L plus m plus 1 h cut, and it will make the state m to m plus 1. Similarly, L minus, if we add this on Lm, it will give us the value L plus m into L minus m plus 1, and we have h cut here, and the state will be L m minus 1. So what is the, so Lx we can write as, from these two Lx we can write as Lx L plus L minus by 2, and Ly we can write as Ly L plus minus L minus by 2y. So first we have to calculate this uncertainty. So what is L plus on the state psi? So let us calculate. So L plus, and we have here A 1 plus B 1 minus 1. So for this state we have A root under L minus m. So since L and m both are 1, so we have L minus m to be 0. So that is why first term will be 0. So it will be 0 plus, for the second term we will have L value 1 and m value minus 1. So we have 1 minus of minus 1, that means plus 1, and here we have L m plus 1 h cut, and the state will be 1 0. So what is the value? So we are getting root 2 h cut b 1 0. And what is the effect of L square on psi? So L square and psi means L plus acting on L plus psi. So L plus psi we have got to be root 2 h cut b, and L plus acting on 1 0. So L plus acting on 1 0, that means we have again root under 2. So we have 2 h cut square b 1 1. So similarly, let us now calculate L minus on psi. So L minus we have 1 for L. So L minus and psi is A 1 1 B 1 minus 1. So if we add the L minus, so we will get root under 1 plus 1, and here we have 1 minus 1 plus 1 h cut, and it will be 1 0 plus b, and here we have root under 1 minus 1 1 plus 1 plus 1 h cut. So this value we are getting this to be 0. So this term will anyway give us 0. So we are getting root 2 h cut a 1 0. So similarly, if we again add L minus on this state, so we will get, as we get for the previous one, 2 h cut square a 1 minus 1. So so what will be the expectation value of Lx? Lx expectation value will be psi L plus L minus by 2 psi. And what is the action of, so we have here psi, half we can take out, and what is the action of L plus on psi? L plus on psi is giving us root under 2 h cut b 1 0, and L minus on psi is giving us put under 2 h cut A 10, and psi this only contains 1 1 and 1 minus 1. So since this 1 1 1 minus 1 and 1 0 they are orthonormal, so inner product of this with this will be 0 and this with this will also be 0. Similarly for this one and this one. So we have Lx expectation value to be 0. In the similar manner, we can show that the expectation value of Ly, that means psi L plus minus L minus by 2y psi, it will also be 0. So now we have to calculate Lx squared. So what is Lx squared? Lx squared will be 1/4 L plus squared plus L minus squared plus, if we have if we recall previous formulas, so we can easily show that this will be L square minus L z square. So this is our Lx squared. So what will be the expectation value of Lx squared? It will be 1/4 expectation value of L plus squared plus expectation value of L minus squared plus 2 into expectation value of L squared minus expectation value of L z squared. So what is this L squared expectation value? If we add this L squared on psi, so we will get A 1 1 B 1 G minus 1. So we will simply first L squared means we are getting this value. So we will have L into L plus 1 h cut square A 1 1 plus L into L plus 1 h cut square B 1 minus 1. So we are getting 2 h cut square psi. So what will be expectation value of L squared? It will give us 2 h cut squared. And similarly, what will be the expectation value of Lz? So for that Lz square expectation value, so first we operate this Lz square on psi. So it is A 1 1 and B 1 minus 1. Now what is this? This is our M value. So if we act Lz on Lm, we get M h cut Lm. So if we act Lz first, so first let us only operate one Lz. So if we operate Lz on this, we will get 1 h cut 1 1, and if we operate on this, we will get minus 1 h cut. So 1 minus 1. And now if we again apply on this, we will again get 1 h cut here. So A h cut square 1 1, and again we will get here minus 1 h cut. So it will be B h cut square 1 minus 1. So we have h cut square psi. So what is the expectation value of Lz square? It is h cut square. So we have this Lz square expectation value, L square expectation value. Now we have to calculate this L plus squared expectation value and L minus squared expectation value. So what is L plus squared acting on psi? This is 2 h cut square B11. So L plus squared acting on psi, it is 2 h cut squared B11. So psi L plus squared psi, it will be 2 h cut square B, and here we have A. So this will be in ket. So A 1 1 plus B 1 minus 1, and here we have B. So B we have already taken out, so we have 1 1 state. So what we will get? We will get 2 h cut square A B. And similarly, what will be the expectation value of L minus squared? L minus squared psi we know to be 2h cut square A 1 minus 1. So it will be 2h cut square. So A and B we don't know if they are real or imaginary. So we have to take here complex conjugate terms. So it will be A star. So we have 2h cut square A, and here we have psi as A star 1 1, B star 1 minus 1, and this term we know it is 1 minus 1. So what will be the value? So we will get 2 h cut square, and here we have A B star. So this is our L minus squared expectation value. So what will be the expectation value of L x squared? So L x squared will be 1/4 here we have 2 h cut square A star B plus A B star, and this LZ square expectation value and L square expectation value. So L square expectation value is 2h cut and LZ square expectation value is h cut. So basically we have 2 h cut square here. Okay, so there is a little mistake. So psi, this is not 1 here. So this is A squared plus B squared. So we have to write here like A squared plus B squared. And similarly for L squared also, here will be A squared plus B squared. So in this it will be multiplied, this 2h cut square, it will be multiplied by A squared plus B squared. So if we simplify this, what we will get? So basically we will get h cut square by 2 A star B plus A B star, and here we have A square plus B square. So this is our expectation value of L x squared. So what is the L y squared term? So L y squared is minus L plus squared, L minus squared, and here we have minus 2 L squared minus LZ squared, and here we have 4. So these terms we have already calculated. So what is the difference between L plus and L minus? So in case of L plus, we have here L plus squared, L minus squared, and 2 L squared minus LZ squared. So this 2L square minus LZ square, and here we have this term to be minus. So L minus squared will be h cut square by 2, and here we have A star B plus A B star, and this will be a minus. So minus A squared minus B squared. So if we simplify this, we have Ly squared expectation value to be h cut square by 2 mod A squared plus mod B squared minus A star B plus A B star. So this is our Ly squared expectation value. This is Lx squared expectation value, and Lx Ly expectation value is 0. So what is the uncertainty in Lx? So it will be Lx squared expectation minus Lx expectation squared. So this is 0. So this term will give us h cut by root 2 root under a square plus b square plus a star b plus a b star. So this is our Lx. And similarly, what will be Ly? Ly will be h cut divided by 2, and here we have a squared plus b squared minus a star b plus a b star. So we have to find the minimum, the value of or the relation between a and b for which this product will be minimum. So we have h cut square by 2, and the product of these two means we have a squared plus b squared. So this we are getting squared minus a star b plus a b star. This term we also have squared. And we also know, so since this state is normalized, if the state has to be normalized, then the squared value of a squared plus b squared, this must be 1. So we can write this as h cut square by 2 root under 1 minus a star b plus a b star squared. So now let us check the options. So what is first option? We have our first option to be a equal to plus minus ib. So option A. So if a is plus minus ib, then we have a value, we can consider it to be half, then b can be minus I by 2, and for this delta Lx, delta Ly value will be h cut square by 2. And now check for option B. For option B, we have A0 and B1. So if we consider this, then we have delta Lx, delta Ly to be h cut square by 2, and here we have 1 minus 2ab. So a is anyway 0, so it will be 0. So it will be h cut square by 2. Similarly, check for option 3. So for option C, we have a root under 3 by 2 and b as half. So for this state, Lx, Ly, this product will be h cut square by 2 root under 1 minus 4 a squared b squared. So it will be 1 minus c4, so it will be half. So h cut square by 4. And let us do for option D. So for option D, we have L equal to plus minus AB. So for that, delta Lx, delta Ly will be h cut square by 2 root under. So if they are equal, so they both have to be 1 by root 2. So we have 1 minus 4 a square b square, and this is 0. So if a and b they have same magnitude, and if they are real, then the uncertainty in them is 0. So product of uncertainty in them is 0. That means they are simultaneously diagonalizable. So when we know from quantum mechanics, so when two operators are simultaneously diagonalizable, the product of their uncertainty must be zero, because if two observable they don't commute, then from Heisenberg uncertainty principle we can state then that the product of their uncertainty at least must be h cut by 2. For suppose position and momentum, we know for them the uncertainty product is at least greater than h cut by 2. So now here for a plus minus b, this product is 0. So that means these two Lx and Ly, for this special value of a and b, if they are same, then they share the same eigenstates and they are simultaneously diagonalizable. So our correct answer here is option D. Okay, so that is it for today's video. So we will meet on our next lecture video.